Hello again. We are now in chapter 5, Constraint Satisfaction. These are combinatorial problems that have some constraints put on them, which make it more interesting. We are going to look into three problems that are solved here with the genetic algorithms. So let's take a look at the first problem. It's called the n queens problem, and this is a problem of placing so many queens on a chessboard, basically the same size. So if the size of the chessboard is 8, there would be 8 queens. We can see that if we run the queens.py, where there is a good solution and there is a solution that has violations. So violation is what we want to minimize in those problems. We don't want to have, in the case of the queens, all the violations should not be there. We don't want any violations. The problem is defined as placing the queens on a chessboard without them threatening each other. So they can be on the same row, the same column, or the same diagonal. And here we see two violations. The two queens are on the same diagonal here. Also, these two queens are on the same diagonals, and these two queens are on the same diagonal. So we have three violations here on an 8x8 chessboard with 8 queens. And this is what the problem will tell us, that there are 3 violations. If we had run the other case, this one, then that would be a valid solution. There would be no violations. So generally speaking, we want to solve the problem of a particular size, find a way to place all the queens, and we're doing it here with the genetic algorithm, where we try to do it with 16 queens on a 16 by 16 board, and the number of possible combination is huge. Also, the number of solution is relatively large, but still it's an enormous search space. If we run this program, it will eventually find a solution, and it will show us the solutions and their locations. But you can perhaps see here, I don't know if I can enlarge it much, but you can see here that the queens are placed. There is basically every column and every row there is a queen, and they never are on the same diagonal. So this is a good solution. Here you can see that we actually found the best solution after maybe 22 generations. We can also see it here. This is the number of violations that we are minimizing. So from 3 to 2 to 1 and eventually 0 in generation 24. This is where we found a good solution, and after this we might have found more good solutions. And at the end you can see that the best solutions are those. The first 10 of them, or sorry, the first 8 of them are actually valid solutions because they have no violations at all. Let's continue with the nurses problem, and this is an example of a scheduling problem which is very common. Scheduling of employees, scheduling of machines in a machine shop, scheduling of classes, scheduling of teams or individuals in a contest, or even scheduling of a conference speakers. And here we see that we have different constraints on the nurses. The nurses can there are 3 shifts per day, and there are some hard constraints, what we consider hard constraints that we never want to violate, which are things like a nurse cannot do 2 shifts in a row, or a nurse cannot do more than so many shifts in a week, or there should always be at least so many nurses and no more than so many nurses within a shift. So we can actually see those here. And then these are the minimum maximum. But there is also another kind of constraint that we call a soft constraint, which is the preferences of the nurses. So for example, the first nurse here prefers to do only morning shifts, and this nurse prefers to do the first 2 shifts. So these are a constraint. So what we call the soft constraints are the ones that we try to satisfy, but if we minimize them, but having a violation of one of these constraints is not going to invalidate the solution. However, having any of the hard constraints violated invalidates the solution altogether. So the way we do it, we give a larger weight to the hard constraints, and a smaller weight to the soft constraint, and we're trying to minimize the whole thing. And solution, the genetic algorithm solution, is going to try to do that. Let's maybe close this window and run that. So what we see here is that at some point this column shows you the fitness, and you can see that at some point this is the minimum. We're trying to minimize the punishment for the constraint. So it starts with a pretty big punishment, and then at some point the cost of the violation or the punishment goes under 10. 10 was the cost of a single hard constraint. So we know that at this point already we are no longer violating any of the hard constraints. These are only the soft constraints that are left, which are the preferences of the nurses. So we are continuing to minimize it, and eventually we go down to 3. So as you can see here is a schedule that was created, and there are no violations of the shifts per week or nurses per shift, but there are 3 violations of preferences, which is acceptable, unless we want to keep minimizing it, and maybe we will get to the point where all the preferences are being satisfied, if such a solution exists. Let's continue with graphs. So let's continue with graphs, and a graph is what you see, for example, here. These are nodes that are connected with edges, and actually they can represent a lot of different problems and sources of information. The problem that we are trying to solve is coloring the nodes in the minimum number of colors, so that no 2 nodes, adjacent nodes, will have the same color. So if there is an edge connecting the two nodes, the edge has to have 2 different colors on the 2 sides of it. And this is a fundamental problem in the field of graphs. So the way we do it, we consider again constraints, hard constraints and soft constraints, where the hard constraint is you don't want an edge to connect the same color to itself, and every violation of this will be more costly. And then the soft constraint is trying to minimize the number of colors. So we use the number of colors as another constraint. So we're trying to minimize the number of colors at the same time that we're trying to minimize the number of violations, which are more costly. So what this program does, it uses a Peterson graph, which is similar to the graph that we see here, and and it starts it has 10 colors, but it's up to 10 colors, and it tries to minimize the number of colors as well as the violation of the nodes having the same color. So or adjacent nodes having the same color. Let me kill this again and run this again. So what we can see here is that we found a solution. You can see that we found a solution, and 3 is the best fitness, and what it means is that there are no violations of adjacent nodes having the same color, because these violations are worth 10 or more. There are only 3 basically soft constraints, which means we use 3 colors. And indeed 3 is the best. We can't go to 2 with this kind of graph. So 3 is the best solution, the minimal amount of colors that we can use to have the best solution. So we found the best solution here. What if we wanted to use a more complex graph? So we can replace this graph with a somewhat more complex one that is called the Misielski graph of order 5 in this case. And if we run that, also we start with 10 colors, we will see that a solution is found with 6 colors. And you can see it here. So you see this is a much more complex graph, and there are 6 colors, and there are no violations of there are no violations, meaning it's a valid graph, but it uses 6 colors. So we see that we were able to solve it with the 6 colors, and in case maybe there are less colors that will work as well, the trick that we can do here is go back to the program and say, you know, we were searching with 10 colors, and we know that you can do it with 6 colors, so let's limit the number of colors to 5. When we do this, we decrease the search space considerably. We have a lot less combinations now, so perhaps this time it will be able to find a solution that it wasn't finding before, because there is a lot less combinations to search over. So if we do this and run this program, it actually finds a solution very quickly, and it does have 5 colors. And we know that you cannot do better than that, but you can see how quick it found it, because the search space is so much smaller. So this was it for the constraint satisfaction, and we will continue in the next video for chapter 6.